Anyways, oh, that hurt. Let's get started. So, last time we had just barely introduced a PDA, a Pushdown Automata. So it was like a finite state machine. It was like a NFA, a non-deterministic finite automata, except for it had access to a stack. And that was a big difference. In every transition, it could read something from the stack, and it also had the option of pushing something onto the stack. And that was the only major difference. So let's look at its exact definition real quick. So a PDA is a six-tuple, where the members of the tuple are right here. Q, sigma, gamma, delta, Q naught, F, where Q is exactly what you expect. It's a set of states. Sigma is your input alphabet. Gamma is your stack alphabet now. So the symbols that you read as input aren't necessarily the symbols that you put on your stack. Common example of a symbol that we had on our stack was like the $sign. We always use that to mark the bottom of our stack. Now our transition function. Our transition function, you tell it what state you're currently in. You tell it what input you're currently reading, possibly nothing, you don't have to read an input. And you tell it what symbol you're popping off the stack, possibly nothing, you don't have to pop it off the stack. So given a state, an input symbol, and a symbol off the top of the stack, you then can determine what state you go to and what symbol you want to push on top of the stack, possibly nothing. Now we did it to the power set because remember, PDAs are non-deterministic. So for a particular state, input symbol, and stack symbol, you can possibly go to multiple different states and multiple different symbols to write onto your stack. They're non-deterministic. So that's why it's the power set of those rather than just to those. Make sense? Mm-hmm. So that's the hardest part of the definition. And then Q naught in Q is the start state, and F is a subset of Q is a set of accept states. And you can have multiple accept states. That definition, clicking, making sense, remembering stuff. Maybe before we go to this, let's really quick draw out one of these things to remind us what they look like.
Power set?
No, PDA.
Oh.
So I'll quickly do the example of the PDA 0 to the n, 1 to the n to remind us of this thing. Okay. So we're going to have our start state. There it is. And then reading nothing and popping nothing off of the stack, we're going to push onto the stack a $ symbol. So that gets us over here. So imagine that we're reading some string 0, 0, 0, 1, 1, 1. There's a string that we should accept. And we'll keep track of our stack over here for that hypothetical string. Is it way too big? It doesn't matter. So by the time we go from here to here, all we did was push onto our stack the $ symbol. So we're right there. Then in this state, what are we going to do? We're going to loop to ourselves, reading zeros. We're going to push a we're going to pop nothing off of the stack, and we're going to push a 0 onto the stack. So every time we read a 0, we're going to push a 0 on the stack. So we read that symbol, pushing a 0 on the stack. We read that symbol, pushing a 0 on the stack. And we read that symbol, pushing a 0 on the stack. So now we're looking at that symbol in our input. Now, I'm going to non-deterministically guess that we're done reading zeros. So I'm going to come down to this next state, reading nothing, pushing nothing, popping nothing. So non-deterministically guessing, hey, we're in the middle. Which gets us down here. Now down here, what am I going to do? Every time I read a 1, I'm going to pop a 0 off the stack, and I'm going to push nothing onto the stack. So now I'm going to read that one, read that one, read that one, and every time I read a 1, I pop a 0 off the stack. So I pop that 0, pop that 0, pop that 0. So now we're done with our input. Reading 3 zeros, still in this state. Finally, we create a transition to our accept state, and our transition reads nothing, and it pops a $sign off the stack, and it pushes nothing onto the stack. And so the only way we can go from this state to this state is if we read as many 1s as we popped off the stack and left the stack empty. So that pops that off, puts us there, and we accept. Good?
The stack has to be empty for it to be accepted, right?
I don't know if that's technically the case.
You also don't have to put the dollar sign in.
Yeah, we don't have to put the dollar sign in, and just guarantees that we used all the information in our stack, helps us reason about it.
Do you have to? You don't have to empty your stack either, right?
I don't think that you have to empty your stack. Matter of convention, we designed them to do it. So in all our machines, we will empty our stack. I don't know if we technically need to for it to accept a string.
So it just has to get to that location somehow.
Yeah, if it gets to this location, then it accepts. Okay, so that was the machine for 0 to the n, 1 to the n. Now let's read this next definition and hopefully make it make sense with this ink. Let's label each of these states really quick to make sense of it. We'll call that Q0, Q1, Q2, and Q3. Q3 being our only accept state. Okay, so now a PDA M equal to Q sigma tau delta Q0 F accepts the string W, where W has n characters. So where W is equal to W1, W2, all the way to Wn, where each of those Wi's are in our input alphabet. Provided that there exist sequences of states, R0, R1, R2, all the way to Rn, and a sequence of, this is the state of the stack. So a sequence of states and states of the stack such that these three conditions are met. The first state that you start at is the start state, and your stack starts out empty. You don't get started out with symbols on your stack. S0 is your stack after your first transition. S1 is what your stack looks like after your second transition. So just to explain it over here, after we went through 3 transitions, S sub 3, our stack was equal to 0, 0, dollar sign. Because we put a dollar sign on here, and then a 0, and then a 0. So that's what our stack equaled after 3 transitions.
On our first transition, didn't it equal just dollar sign? After the first transition, from Q0 to Q1?
Yeah, our first transition was just dollar sign.
So,
Our second one got a 0 dollar sign, and our third one got 0, 0 dollar sign.
okay. I don't know if I just like misheard the words you're saying, but you said after the first transition it has to be empty?
Oh, sorry. Now, what I was trying to say is S0 has to be empty.
And S0 is the state after the first transition?
No, S0 is a state after 0 transitions.
Okay.
S1 is a state after 1
That makes
transition.
more
Okay,
sense.
yeah, sorry, I parsed that wrong. Just to be super clear, for our case here, S0 was the empty state. S1 after 1 transition, we were at dollar sign. S2 was 0 dollar sign. S3 was 0, 0 dollar sign. S4 was 0, 0, 0 dollar sign. And then that was S5, that was S6, that was S7, that was S8. And after S8, we were done. Okay, so, accepts a string W, where W is all those individual characters, provided that there exists some sequence of states, R0, R1, R2, Rn, and some sequence of states of our stack in gamma star. Remember, gamma is all your possible stack symbols. So gamma star just means it's some combination of stack symbols. Each of these are in gamma star. Okay, such that you start out in your start state, and your stack starts out empty. And then for each transition, for each I between 0 to n minus 1, we could have also done I between 1 and n for each of the n transitions. So notice that I increments over n values. So for each of the n transitions, we have the next state and the next symbol on top of your stack is in the set of states and symbols that you can reach from your previous state, reading your current input with your previous top of your stack. Where S of I, your stack before you read the symbol, was A and then T. T is going to be a string of symbols. A is one symbol, T is a string of symbols. And S of I plus 1 is BT, where A and B are just input symbols, possibly nothing, possibly the empty string, and T is some string of symbols. And then finally, and then Rn is in your set of accept states.
Step number 2 is not clicking right away.
All right,
Maybe you just need
let's write a particular case
Okay.
over here. So let's write the case where we are one of the ones where we're going from Q1 to Q1, right?
Mm-hmm.
So what we're saying is that Q1 and the symbol that we used to have on top of the stack, going from here to here, the symbol that we popped off of the stack, I should say. Oh wait, no, and the symbol that we're pushing onto the stack, sorry. So I'm gonna write this, I want to underline it, I'm gonna write this out for a particular case.
Okay.
So Q1, because that's the state that we end up at, and what do we push on? 0, is in the set of states that can be reached from delta if we give it Q1, and we give it 0 as an input symbol, and we pop off the stack nothing. So if it was a case where we were going from here to here, so if we're going from here to here, B is equal to 0, A is equal to the empty string, and T is equal to 0, 0, $sign. So we have R sub I plus 1, and B is in the set of states that we can reach from the previous state, the symbol that we're currently reading, and what used to be at the top of the stack. Or what you popped off the stack. Probably a better way to say that.
Okay.
Where, here's what your stack used to look like. So our stack used to look like this, and now it looks like this. I'm going to rewrite S3 in a funny way. Our stack used to look like this. Empty string, 0, 0, $sign. And now it looks like this. 0, 0, 0, $sign. There's your A, there's your B, there's your T, there's your T.
Okay, so A is what we are
Popping off.
and B is what we're pushing on.
Correct.
Okay.
Yeah, it's dense. But that's the densest definition we'll have today. Okay? So, more examples?
Yeah.
Before we continue more examples, let's actually write out this machine explicitly. Let's write out a PDA explicitly once, and then we'll never do it again. And you'll see why we'll never do it again.
Okay.
So let's write this machine out explicitly. So if this is machine M1, well, we'll just call M. Then M is equal to the tuple Q, Q sigma gamma delta Q naught F, where Q is equal to, when we write Q explicitly, that's going to be Q naught, comma, Q1, comma, Q2, comma, Q3. Q3. Our input alphabet is going to be what?
Just 0 and 1.
Just 0 and 1. Our stack alphabet is going to be what?
0,
$sign.
and $sign.
0, 1, and $sign. No 1, just 0 and $sign. Right? We never push 1s onto our stack. We only count the zeros and then pop off the zeros as we read the 1s.
Would it be like an incorrect definition to put 1 there though?
No, you can put it there. It just so happens we don't use it.
Right, okay.
Yeah. And then Q naught is Q naught. We already have that stated. F is equal to the set of accept states. In this case, that's just the set containing Q3, right? And then, and delta is given by the following table. And this is why we never bother writing these things out. Let me see if I can remember the order. We just stack at the bottom, input at the top. we track stack. Here we track the delta over here. Here we track input. Okay. Split that up. Split that up. Our possible inputs are empty string 0, 1. And then for each input, we have 3 possible stack symbols. 3 possible things that we pop off the stack. So when we read the empty string, we could possibly pop the empty string off the stack. We could possibly pop 0 off the stack, or we could pop $sign off the stack. Similarly, when we read a 0, we could have popped an empty string, we could have popped a 0, or we could have popped a $sign. And when we read 1, same thing. And then here, in each of these, we've got to write hopefully I have a space trapeze. Smarter to have a bank. Satellite blue one. So now down here we write the states we could possibly get to, or the states we're coming from, I mean. Q0, Q1, Q2, Q3, and then in each square we write the set of possible states we could get to from that state with that input symbol. So reading this as our input, popping this as our stack, being in this state, where could we possibly go? That's what we're filling out in this table, right? So for this first transition, we're at Q0, so we're at Q0. We're reading as our input epsilon, and we are popping epsilon off the stack. And what are the possible places we can go? Turns out it's just one, so it's the set containing the place we can go to Q1, pushing a $sign on top of the stack. So that's a set containing the tuple Q1 $sign.
Okay.
Right? And then all these other ones are empty because that's the only valid transition we have. Right? So I could put empty set there, empty set there, empty set there, blah, blah, blah. Not going to bother writing all the empty sets. Then, at Q1, reading an epsilon and popping an epsilon, we could go to Q2, pushing an epsilon. So in Q1, reading an epsilon, popping an epsilon, we can go to Q2, pushing an epsilon. So we can go to Q2, pushing an epsilon. Or, reading a 0, popping an epsilon, we can go to Q1, pushing an epsilon. So, sorry, reading a 0, popping an epsilon. So in this one, I'm going to scoot this line over to give me some space here. So here, we can also go to back to Q1, pushing,
0?
or not pushing, but popping an epsilon. Oh, but this is what we push. Sorry, pushing a 0. So from Q1, reading a 0 and popping an epsilon, you can go to Q1, pushing a 0. And then the rest of those would be empty sets. Finally, Q2, we have 2 arrows again. So reading an epsilon, popping a $sign, we can go to Q3, pushing nothing. Or reading a 1, popping a 0, we can go back to Q2, pushing nothing. Right? And then Q3 has no transitions out of Q3. So here is our full transition table. Notice that almost the entire table is just a bunch of empty sets, empty sets, empty sets. And it's kind of annoying because it's really hard, because this really needs to be something three-dimensional, and we can't draw in 3 dimensions, so
Right.
we have to make it really ugly 2-dimensional. And so that's why we hardly ever explicitly write out these machines, and we won't bother doing it again. But you see how the table encodes the transition information here, and theoretically, if I gave you one of these, you should be able to reproduce the table, or if I gave you the table, you should be able to reproduce one of these. All right. So there's writing one machine out explicitly. A couple more examples with these machines. WW reversal. Let's see if you guys can remember how to do this one. Walk me through it. Assuming our language is zeros and ones. Do you remember what this is?
It's a string and then reverse it. And
Yeah, some string of zeros and ones followed by that same string in reverse order.
Right.
Right?
Mm-hmm.
So walk me through it. Start state, then what?
I'm trying to remember how to do it.
Could you create a scenario? Maybe that helps.
So an example of a string you want is 0, 0, 0, 1, 1, followed by 1, 1, 0, 0, 0.
Could it also be 0, 0, 1, 0, and then like 1, 1, 1, 0? You know, like it could go up and then down, like.
It just, whatever this is, this needs to be the same thing in reverse order.
Yes, but it could be, like, for instance, 0, 0, 1, 1, 0, 0, 1,
0, 0, sorry, say it again.
So 0, 0, 1, 1, 0, 0, 1, 1, 0, 0.
Yeah, so that split right here, you have that string and that string reversed.
Okay.
Yeah, perfectly fine.
So we'd start with a read an epsilon, pop nothing, and then push a $.
Right, so start by putting the $sign on the bottom of our stack. That gets us to this state. What do we want to do here?
I think we're gonna have 2 arrows going to Q1. I think we read a 0, pop nothing, put a 0 on, and if we read a 1, then we pop nothing.
Perfect.
Put a 1 on.
Whatever we read, just push it on the stack. So if we read a 0, push a 0 on the stack. If we read a 1, push a 1 on the stack.
Mhm.
So if we were doing the string 0, 0, 1, 1, 0, 0, then our stack so far would be, you start by putting the $sign on there. Then in this state, we're going to read the first half of the string. So we're going to push a 0, then push a 1, right? Then,
Do an empty.
right, non-deterministically guess that you're at the middle of the string.
Right.
Can you explain how to say that? The empty and then like.
Reading nothing, push nothing off the, pop nothing off the stack, and push nothing on the stack. So now in this state, what do we do?
Also have 2 arrows going to itself. You'd have, if you read, if your input is a 1, then pop a 1 off the stack, push nothing.
Perfect.
And
Same
then
thing for 0. Right, so now, just make sure whatever you read is sitting on top of the stack.
Oh, that makes sense. You can push and pop in the same motion.
Right.
I finally got that connection.
So now, when you come down here, you pop every time you see a 1, and you pop every time you see a 0. So this is what our stack looked like when we got to the middle. Now when we come down here, when we read that 1, we better pop a 1 off. And then when we read that 0, we're going to pop a 0 off. And when we read that 0, we're going to pop a 0 off. That'll get us back down to our $sign. And finally, this transition always looks the same. Reading nothing, we're going to pop $sign, push nothing, which gets us to our accept state. Right? Good? Now let's try the complement of that. So now we want to accept a set of strings that isn't in WW reversal.
Okay. first two states are gonna look the same.
So we'll start with, you're saying start with a start state,
Yeah.
and you're saying first we're going to want to read nothing, pop nothing, and push on a dollar sign.
Can you like make all of the states accepted except for the last one?
No, that doesn't work on non-deterministic machines. You can't just toggle those states.
Not even in this case.
Not even in this case.
Oh, right. I see that now. Because you could come up with whatever you want and it could technically be a good path going. Got it.
I think we have the same two arrows, where it's like read 0,
You're saying here,
pop nothing.
if we see a 0, we push a 0 on. Oops, we pop nothing. And we push a 0 on. And if we read a 1, we pop nothing. And we push a 1 on.
Yeah.
Okay?
And then go down to the epsilon arrow, read nothing, yeah, non-deterministic.
Doing nothing, pop nothing, push nothing, which gets us down here. Okay?
Except I'm not sure now because
We just need at least one mismatch, right?
right, it just in my head I'm thinking I'm like making it so it has to be half and half, but that doesn't make sense, I guess.
Right, so I was going to come back to that detail, but we can approach that detail right now. What are all the strings, if you were to try and describe in words all the strings that are in this set, what would you say?
I would think it has to be like it's everything that's not a string and then the reverse of it.
Right, so try and state it in terms of what it is. Like you're saying we need to non-deterministically guess the middle here.
But we don't.
No, we do because well.
But who's to say that the string has a middle?
Right, it can be an odd number.
So in here we have odd strings. In here we only had even. In here we had odd. So this needs to accept all the odd strings or the even strings with a mismatch. So it's actually easier to have a special case for the odd one and to just say on odd strings, we come up here to this, and this machine just accepts it if it's an odd length.
Alright.
So reading anything, reading any input symbol, sigma, pop nothing, push nothing, which will take you over here. This is our accept state. And then reading any input symbol, push nothing, pop nothing, which will take us over here. So if it's odd, we're there, even, odd, even, odd, even. Who cares about the stack? We don't need the stack. We could do that machine with a simple PD or a simple DFA. So now this will handle all of our odd strings. So we have a way to handle our odd strings.
Okay.
And now we can think about this path as just even strings.
Okay,
That's what I was trying
makes
to
sense.
hint at without just saying it.
Okay, I think that third state is going to have the same arrows that we have on the other one.
All right, so you're saying it's okay if we have some matches. So if you get a 0, that's fine. You can pop a 0 and push nothing. And if you get a 1, you can pop a 1 and push nothing. That's fine.
But if you get, so if you get a 1 and then you try to pop a 0, then you
have a
you can
mismatch.
accept it as a mismatch. So that would be the other option. And
So then if we have a, like you're saying, if we have a 1 and we pop a 0, or if we have a 0 and we pop a 1, then we can come over here
and accept it.
and almost accept it.
Oh,
Now we need this now. We've had a mismatch once we get to this state.
Okay.
So now we don't care what the rest of the string is, as long as we make sure that we non-deterministically guess the middle correctly. So here we say, I don't care what the input is, pop whatever there is, I don't care what you pop, and push nothing.
So that's implying that you still have to clean out your stack.
Right, because you still better have as many symbols as you're reading that you have on your stack. That's all you're making sure stays the same. So you're saying, I don't care what I read, and I don't care what I pop off the stack,
Oh, we have to finish.
but I better be able to read a symbol for every symbol on the stack, otherwise we did not guess the middle correctly.
I see. So we gotta finish reading.
So we gotta finish popping off the stack and reading the input symbols.
Got it.
And then if, when that's all said and done, once we're finished reading our input symbols, if we also finish reading off the stack, then our last transition here, we should be able to pop a $sign off the stack, pushing nothing, and get to our accept state.
Yep.
If we happen to still have another symbol to read when we get here, we crash, and we guess the middle round.
Why can't we just have that fourth state be an accept state, and
Right.
then we wouldn't even need the odd?
Yeah.
Like, I'm trying to think of an exception, like, that disproves that.
Right, so we'll go through that really quick. So let's look at the string 0, 0, 1, 1, 0, 0. We should not accept this, right?
Mm-hmm.
So what could I do? I could read 0, 0. So I'll write my stack out as we go. So here's what I'm going to do. Going from here to here, I'm going to read a 0, 0 and push them onto stack.
Mm-hmm.
Then I'm going to guess that this is the middle and come down here. I read a 1 and I pop a 0, which gets me straight over here.
I see.
So now I pop the 0 reading a 1, pop the 0 reading a 1, pop the $sign reading a 0. Well, then I'm going to crash.
You're supposed to crash, and so you can't accept, that can't be an accept state. Only the last one.
Maybe it would just so happen that that worked. I don't know. I don't think so. I think we could think up an exception if we thought about it.
Maybe there's a string it should accept that it doesn't because of that?
Because basically, you're not guaranteeing that, I mean maybe this does work, but the reason that it's kind of confusing to think about it is because now you're not thinking about, we're good once we get to an accept state. Now you're thinking about, do I ever accidentally get out of that accept state and crash?
Mm-hmm.
So you might be okay. It's just hard to reason about.
Yeah, it's a lot
Because
easier.
once you get there, you're not for sure safe.
Right.
But I think you might be right. I don't know.
Yeah, it's a lot easier to reason it and like dividing it between odds and evens and stuff like that.
Yeah, anyways. Here we have before for sure works. I suspect that this works, but I'm not positive. Alright. And then we talked about the string WW, doing that machine.
We couldn't do that one, right?
And you can't do that one, yeah. So we tried to do it, we couldn't do it, we just decided, okay, it's too hard. Most likely impossible.
You can do it with 2 stacks, right?
You can do it with 2 stacks. But when you have 2 stacks, you have a Turing machine.
Right.
So if you could create a program that recognized strings like this, then a Turing machine could do it. And you could definitely write a program to recognize, did I get the same string twice?
Right.
Yeah. So yeah, as crazy as it is, adding one more stack gives you a whole new level of computation power. Giving you a million stacks after that doesn't change anything. Okay, and then WW complement, I don't know. Do we want to do that one?
Well, that one's at least possible, right? With 1 stack?
Yeah, we can do that one with a PDA.
That would be cool to go through a mental process.
All right, let's go through. So this one, we're going to come to the start state.
It's $1.
Now we're going to have the machine that comes up here is odd. So accepts it if it's odd length, because we'll accept all our odd length strings. And we know how to do that, so don't need to write that one out. Otherwise, we read nothing, we pop nothing, and we're going to push the $sign onto the stack. Now this one is kind of tricky. How on earth do we do this one? It's actually a good one to kind of think about. So if it's not WW reversal, then that means, so writing out our string, so here's the middle, somewhere in there. So here's W, and here's W again, in terms of our characters. In order for it to not be in WW, then we need to find some character here that mismatches a character here. Right? And we're kind of stuck because how do we count that this character mismatches this character? How do we make sure that that lines up and happens?
Right.
And so this one's actually kind of a tough problem until you have the special insight that this distance right here, I'm going to color in purple, is the same as this distance here plus this distance here. And so what we're going to end up doing is to make sure that because somewhere along the way we need to check that two symbols mismatch. But we need to make sure that the two symbols that mismatch are this distance apart. Right? We can't just make sure that, we can't check that these two symbols mismatch. We got to make sure it's these two symbols that mismatch. They've got to be separated by this distance. Now, how are we going to ensure that they're separated by this distance? With just a stack. And so the trick here is reading from here to here. I'll underline at the bottom when we push x's. I'm going to push an x every time I read an input symbol. I'm going to push an x on the stack. Going from here to here, I'm going to pop an x off the stack. Then my stack's going to be empty. Once my stack's empty, I'm going to push again from here to here. I'm going to non-deterministically guess that we're at our mismatch symbol.
Oh, okay, so this is like retry every scenario? Or like, That is tricky.
And then I'm going to keep pushing from here to here. And then I'm going to pop from here to here.
And then you try that for every single set.
And if all your pushes and all your pops come out perfectly, then you were separated by the right distance.
It's so inefficient. Drives me nuts.
Well, you just have one stack to use. And you just have to slowly push things on and pop things off as you go. So let me try and write this a little bit more compact so that we don't take up too much space. So reading nothing, popping nothing, we're going to push on to our sign. Now in this state, every time I read 0 or 1, every time I read an input symbol, I am going to push an X on my stack. And I'm going to do that until I non-deterministically guess this is the symbol that's going to mismatch. So then I read my symbol that's going to mismatch. And we're assuming that we're talking about binary strings. So if I read a 0, I'll come up here. So this is, we read a 0, and we won't touch the stack right there. And that brought us up here. If we're going down here, this will be, we read a 1. So now if I'm in this state, I know I ultimately need a mismatch with a 1. If I'm in this state, I know I need to ultimately mismatch with a 0. Right? So then, in this state, for every symbol I see, I'm going to pop an X, and I'm going to push nothing. And similarly down here, for every symbol I see, I am going to pop an X and push nothing. Once I see the dollar sign, I pop the dollar sign and I push it back on to mark the bottom of my stack. Similar thing here, if I see the dollar sign, I pop the dollar sign and I push it back on. So that was making this transition right here. Now, for every input symbol, I'm going to pop nothing, I'm going to push an X. And for every input symbol, I'm going to pop nothing, I'm going to push an X. And that'd be a non-deterministically guess, once again, that we're at our mismatch. So now, if I read a 1, I'm going to pop nothing, I'm going to push nothing, leave our stack alone. Similarly, if I read a 0, I'm going to pop nothing, I'm going to push nothing, which gets us back to this state now. Now in this state, what do we need to do? We need to finish popping. So now in this state, for every symbol I see, for every input symbol I see, I am going to pop an X and I'm going to push nothing until finally we get to an empty stack. And then reading nothing, popping the dollar sign, pushing nothing, gets us to our accept state. So let's run through a scenario seeing this in action.
Yeah.
Because it's kind of a harder one to follow. So the string we'll do is 0, 0, 1, 0, 0, dot, 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 and then 0, 0, 1, 1, 0. So not WW. These are our two symbols at mismatch. Okay. So let's write our stack over here as we go through these. Okay, so obviously if I wrote something up here odd length, we'd accept it. So this is going to be taking this route since it's even length. So going from here to here, we push the dollar sign onto the stack. Now, for every input symbol, until we get to our mismatch, we're mismatching that with that, we're going to push an X on. So here, going here, going here, going here, we're just pushing X's. And we're going to do that 3 times. With me so far? Now we non-deterministically guess this is a symbol that's going to mismatch. It's a 0, so we go up here. Now we are going to pop until our stack is empty. So we're going to pop, 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 reading these symbols. So we read that, we read that, we read that. Now we're reading this one. Let me separate those. This is 1, 1, 0. This is our mismatch. So now our head, we're reading this one. And that was right here. Now our stack's empty. So going from here to here, we read nothing, popping that dollar sign and pushing it back on. Now in this state, we read whatever we're reading, which is a 1, which gets us to here, and we push an X on the stack. Now going from here to here, we just read our mismatched symbol, not touching the stack. And now, for every symbol we read here, we pop something off the stack. So we read our last symbol 0, we pop X off the stack, now our stack's empty, and we can accept.
Yeah, I can see how this makes a lot of sense, because you're really only looking for one scenario, where in the other case, we're looking for all the scenarios to work.
Right. If we had switched this to 1, 1, where there's multiple scenarios, it wouldn't have changed anything in how we process this whole string.
Right.
Because we still said these two are going to mismatch. We could have also used these two are going to mismatch, or these two are going to mismatch.
That's really cool.
So yeah, there's our machine. Kind of a big one. All right. Should we do this last one? Another example?
Yeah.
So this last one, we're accepting the strings A I times followed by B J times followed by C K times, where we either have the same, where I and J are the same number or I and K are the same number. So either we have the same many A's and B's or we have the same many A's and C's. With me? All right, so we've got our start state. There she is. What are we going to do?
Well, we're going to read an epsilon.
Reading nothing, popping nothing, we'll push a dollar sign. Gets to this state. Now what should we do in this state?
You have an arrow going to itself. Read A, pop nothing, push A.
If we read A, we'll push an A. So basically we're counting how many A's we see. Perfect. All right, so this state counted how many A's we have. Now what?
Maybe we'll just have two arrows going to do two different states.
Right. So we'll have an arrow.
Read
down
nothing,
there.
pop nothing, push
And
nothing.
we'll have an arrow down here. Read nothing, pop nothing, push nothing. Read nothing. Oops. Read nothing, pop nothing, push nothing. Okay, what's this state going to do?
That one's going to make sure it has the same number of B's as A's.
Perfect. So this one, every time we see a B, we pop an A and we push nothing. Okay. And then what else?
Done.
Let's follow through this thinking and then go back down.
Yeah. And then I guess we'll like non-deterministically guess we're done with B's.
Right, that works. Epsilon, epsilon, epsilon to this state.
And then we'll just read a C, pop nothing, push nothing.
So we can read a C, pop nothing, push nothing, just read all our C's.
And then go to an accept state with epsilon, read nothing, pop dollar sign, push nothing.
Perfect. So this one was making sure, this branch of the computation is making sure our A's and our B's, we have the same amount of A's and B's. So we count our A's here. Every time we read a B, pop an A. That way we have the same many A's and B's. We don't care how many C's we have. The stack just better be empty by the time we accept. Now down here, you were thinking we need to match the A's with the C's.
Right, so here we're going to go through all the B's.
So here, when we see a B, we don't care. Pop nothing, push nothing. Non-deterministically guess when we should go to our C's. When we see our C's, we're going to pop an A and we're going to push nothing. And then finally go to our accept state on nothing, dollar sign, pushing nothing. Which I'm sure is what you were thinking.
I just felt really inefficient because I have so many like read nothing, pop nothing, push nothing arrows.
Yeah, we're not really worried about efficiency. We're just worried about proving what things can and cannot do. Complex theory is like chapter 5 of the book.
Complex, is that where you go over efficiency?
Complexity theory, yeah, where you care about efficiency. All right.
That'd be an awesome class.
Yeah, I just don't know how much of it we can do without that one. You kind of need to have taken advanced algorithms for. You need to know big O notation, and it's hard to do an analysis of algorithms without some Calc 2. So that was a bit harder. Because you need to be able to analyze how fast sequences grow, is essentially what it is. I don't know if you've done Calc 2 yet.
I have.
Yeah.
I'm a little bit iffy on sequences, but yeah, that makes sense.
Okay, cool. So now the next thing that we're going to be demonstrating, the last thing for this section, is that pushdown automata and context-free grammars are one and the same thing, so that they're logically equivalent. Remember that we started out this with context-free grammars, and we've been talking about context-free languages. So basically we're proving that a language is context-free if and only if there is some PDA that accepts it. That's what we'll essentially be showing here. Now we're not going to do full-blown proof of this. We're just going to give you the big idea of the proof one way, and then the other way on the proof we're not even going to bother with because it is absurd.
Alright.
So we're going to show that given a context-free grammar, we can construct a logically equivalent PDA. We're not going to show that given a PDA, we can construct a logically equivalent context-free grammar. The proof is in the book. It's just a massive proof, and there's 2 proof by inductions inside the proof itself. So it's a big proof, and it would take like 40 minutes to an hour just to do that proof, which is why we're not going to bother with the other direction.
Right.
Because I don't think that there's like a lot of insight to be gained from it. So first, let's just do an example before we get into the proof idea of converting a context-free grammar into a PDA. And the grammar I have written here, doesn't really matter which one we use, but I'll just use one that I have written, unless there's a particular one you guys like. Then we have T goes to TA and the empty string. Okay. And maybe let's walk through generation of a string on this really quick, and then that'll probably help you get the idea for how our machine's going to work. So when we generate a string with a grammar, what do? We start out with the start variable, s, right? And then we have an option. We can replace s with ATB, or we can replace s with just b. So in this one, we'll replace s with ATB. Why not? All right, now we got that t. We can replace that t with TA, or we can replace it with the empty string. I'll replace it with TA. So now we got ATAB. And I'll replace it with an a one more time. So then we have ATAAB. And then I'll replace it with the empty string, giving us string AAAB. Not the most interesting grammar in the world, but that's how we generate the strings. The idea for how we generate our machines is we're going to keep track of whatever this is with our stack. So we're going to manipulate our stack, so our stack's going to start out looking like S, and then it's going to switch to looking like ATB, and then it's going to switch to looking like this, looking like this, looking like this, for accepting this string, until we get rid of all our variables, and then when this is all that's left on the stack, then we'll read our input, matching it up with each symbol on the stack. That's roughly our idea. Maybe better to just start writing it rather than explaining the idea. I'll write the machine right here. So our machine, we'll start out with, here's the start state. First thing we're going to do is reading nothing, popping nothing. We're going to push a $sign onto the stack, so the stack starts out empty, right? And then, after that, we're going to reading nothing, popping nothing. We're going to push the start variable onto our stack, whatever S is here.
Okay.
So then S is going to be on our stack, like that. And that gets us here. Now, since I have the rule, let me draw this state really big, and you'll understand why. Now, I have the rule that S can be replaced with ATB, right? So I'm going to create this rule where, going from here to here, reading nothing, we can pop an S off the stack and we can replace it with B. That gets us here. And then on the next one, reading nothing, popping nothing, we're going to push a T. And then here, this is actually going to circle back around. So I'll just start like that. Reading nothing, popping nothing, we're going to push an A, and then this is going to circle back around, like that. So ultimately, what did we do? On this whole loop, we popped an S off of our stack, and then we pushed on a B, then a T, then an A. A B, then a T, then an A. So now our stack is ATB $sign. Replace S with ATB. You with me?
Yeah.
We could have also, reading nothing, popping a T, pushed an A, and then reading nothing, popping nothing, pushed a T. So going on this loop, we would have popped a T off the stack and then pushed on a then a T, or ultimately pushed on a TA. Right? Now we could have also had reading nothing, we could have popped a T off the stack and pushed on a B. Reading nothing, we could have popped off a T and pushed nothing, an epsilon. So far we've gotten all 4 of our rules.
I don't get how you're getting read nothing, pop off a T, and push on a B. Like, isn't that?
Oh, thank you, that's an S. Good catch. Yeah, sorry. So we should have each of these 4 rules. S being replaced with ATB, S being replaced with B, T being replaced with TA, and T being replaced with epsilon. I have those 4 rules, right? Now finally, for each terminal, we're going to add a new rule. If I read an A, I want to pop an A off the stack, push nothing. And if I read a B, I want to pop a B off the stack, push nothing. So we only read terminal symbols that are on the stack, and we pop them off as we read them. Make sense? And then finally, if our stack is empty, notice that our stack starts out with the start symbol on it. We only pop symbols off, ultimately, if they were terminals. So the only way that the stack can get completely empty is if all our variables were ultimately converted to terminals, which is the same thing as a grammar generating a string. A grammar only generates a string when all the variables are turned into terminals. So when the stack is empty, pop the $, push nothing, then we can accept. So let's go over it for the same generation that we had before. We had S went to ATB, went to AATB, or ATAB, went to ATAAB, went to AAAB, right? That's a string that the grammar can generate. So this machine better be able to accept this string. Let's run this string on this machine and make sure it accepts. So going from here to here, we push the $. Going from here to here, we push S. Right? Now we're going to take this loop here. So we're going to pop the S, and we're going to push a B. And then we're going to push a T. And then we're going to push an A. And that gets us back here. Now, notice that the only thing we can do now, we can't do this loop again, because our top symbol isn't an S. We can't do this loop again, because our top symbol isn't a T. We can only do loops where our top symbol is an A, which is to read an A. So now, here, I'll write my string that we're reading right here. We're reading A, B. So far we've read nothing, so we're on this input symbol. Now we have to take this loop, reading an A, popping an A. Right? That's the only thing we can do. So then we'll pop that A, and we read that A, so now we're pointing here. Okay. Now the top symbol of our stack is a T, so we're going to take this transition or this transition. Obviously, in our case, we're using this transition. So I'm going to pop the T off, going from here to here, and push an A on. And then going from here to here, I'm going to push a T on. Once again, T's on top of the stack, so I'm going to take that exact same loop again, pop the T off, push an A, and then push a T. And then I'm going to take this loop with the T, replacing it with nothing. So reading nothing, pop a T, push nothing, which then makes the stack look like that. Then I'm going to read an A and pop an A. So I'm going to read that A and pop that A. Then I'm going to read that A and pop that A. Then I'm going to read that B, pop that B. So now I'm done reading my input, then read my $, or pop my $, going to my accept state. Cool. That's the big idea on how these work. So I'm not going to bother doing the proof that every context-free grammar can be converted into, well, we'll write down the in general idea, I guess. Now you've seen a particular example, and I think you'll be fine.
Right.
Okay. So in general, we have anytime I want to go from some symbol, let's see, what does he usually call them? Q to R. Anytime I want to go from some state Q to some state R, popping a lowercase a, or reading a lowercase a, popping a capital A, and pushing some string XYZ. Then we can simulate this same effect by doing what we did over there. I can do Q goes to some other state, reading little a, popping big A, pushing X, then going from here to here, reading nothing, popping nothing, pushing Z, then reading nothing, popping nothing, pushing X, and then finally coming back to here, which is state R, reading nothing, popping nothing, pushing, that is a Y, that is an X. So in general, anytime I want to read little a, pop big A off the top of the stack, and replace it by some set of symbols X, Y, Z, I can simulate that with something like this.
So simplified.
Right, so just, I'm going to use this notation here in a sec, so this is just explain what that notation means. So this equals this, so because the proof of the idea is, the machine we use is, we start up here, in Q sub start, then going from here to here, we're going to read nothing, we're going to pop nothing, and we're going to push onto the stack $, which gets us to here, right? And then here, we're going to have a loop where reading nothing, we're going to pop A and we're going to push on W, and reading little a, we're going to pop A and push epsilon. And then finally, going from here to here, read nothing, pop nothing, push, or read nothing, pop $, push nothing to get to our accept state. So we're going to have this, where we have a rule like this, for all rules in grammar. And we're going to have a rule like this for every terminal A. And that's all you do. So whatever grammar you're given, like the one that we had there before, notice that that's exactly what I did. I generated a loop back to the state for each rule in the grammar that looked like this, reading nothing. And then for each terminal in the grammar, we added a rule like this. And that construction is basically the proof that for any grammar, here's a machine that you draw. And it's that simple. And like I said, we won't do the converse because it's massive. So we'll take it for granted from here on out that we have proved that a language is context-free if and only if some PDA recognizes it.
All right.
Okay? All right, our next concept now is going to be proving that languages are not context-free now. You might remember we proved before that some languages were not regular. And do you remember how we had to do that?
So, pumping lemma?
With a pumping lemma, yes. And so now we're going to talk about a more advanced or a more complex version of the pumping lemma. Do you remember the pumping lemma from last time and roughly how the argument went?
Not exactly.
Let's briefly re-go over that argument. So this is going back to proving that a language is not regular. So proving that no DFA could recognize the language of 0 to the n, 1 to the n. That was a language that was not regular. Right? And how did the proof go? The proof went along the lines of let's pretend that you did have a machine that was a DFA that recognized this language. Then your machine has to have some numbers of states in it, call it P. Right? So now consider the string 0 to the P, 1 to the P. Since your machine only has P states in it, then when the string, your machine is reading the first 0 P's, it has to loop somewhere. It's reading the first 0 P's. And that loop has to have at least one character. And so if your loop has a size of, I don't know, K, is the size of your loop, then your machine will also accept the string 0 to the P plus K, 1 to the P, which is not in that language. And so it's accepting strings that it shouldn't. Basically, we can take that loop as many times as we want.
Right.
So that's what we were able to do with DFAs. We were able to say that there's always going to be a long enough string that you get a loop somehow. And it's that loop that makes it we can pump up the string bigger and bigger, and it better still be in your language. All regular languages have strings that can be pumped up like that. This is not a string that can be pumped up like that, so it's not in a regular language. Well, similarly, we're going to find out that context-free languages also are able to be pumped up in some manner. And so they're going to have this property that you can kind of do a similar sort of pumping up thing. But this time we're going to reason about them in terms of their grammars rather than in terms of their machines. Okay?
Right.
So let's jump into that, the pumping lemma. Before we go into the pumping lemma, I need to remind you of Chomsky normal form. Spent a lot of time on this last time. Chomsky normal, I think it's last time, maybe it was the time before. But Chomsky normal form, I told you that oftentimes converting a grammar to Chomsky normal form makes it a hideous grammar, blows it up, tons of rules, but it makes it easy to prove things about the grammar. So Chomsky normal form says all your rules are going to be one variable goes to two variables, or one variable goes to just one terminal, and only your start variable can go to the empty string. No other variable can go to your empty string, and you can't go back to your start variable, which I let you go back here. Crap. This is not in Chomsky normal form. But I already wrote this out as an example, so we'll use it for now. But I can't believe I did that. That's terrible. Bad example. Anyways, Chomsky normal form, since it has a property that every variable either goes to two variables or every variable goes to one terminal, then in our parse trees for generating a string, if I have a part, this, you understand what I mean by parse tree? A tree like this?
Yeah.
We're saying the variable you're replacing it with, so we can take S and replace it with AB. Maybe make sure we understand what this tree is. You see how this tree is one way we can generate a string in this language? And this tree over here is another way that we can generate a string in this language. Although that's not what that was meant to be. Sorry, just paying attention to this one. This is a bad example for a lot of reasons. Wow. Hopefully it doesn't confuse you. Okay, anyways, so here's a parse tree for it. Now notice, how many symbols does this parse tree generate? 8. So if you have a grammar in Chomsky normal form, and you're going to generate a string that has 8 symbols, what is the shallowest your tree can be? Let me try and make that make sense for you. So if we are in Chomsky normal form, so here's our start symbol, whatever it is. When we replace our start symbol with variables, we're going to replace it with 2 variables. I don't bother with arrows, we'll just do this. You with me? And then for each of those variables, I can replace it with 2 variables. And then for each of those variables, I can replace them with 2 variables. And then finally, I can go through and replace all my variables with the terminal. So then that gets a terminal, 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 terminal. And we're done, and we have our string. You with me?
So that's the whole point of Chomsky normal form, to get that.
Yeah, your trees are in this form. Your parse trees will always be in this form.
Image. Yeah.
When you make them as shallow as possible. So notice, what is the height of this tree? It has a height of 1, 2, 3, 4.
It's just divided the number.
It's just basically the number of steps you had to take to get back to your start.
Are you saying you can do that for every 8-digit string?
I'm saying any 8-digit string generated by a grammar in Chomsky normal form, when you look at its parse tree has to have a height of at least 4. 1, 2, 3, 4. Notice that this one's not really Chomsky normal form, but it still has that same property. Notice that this one, what's the height of this tree? The height of this tree is 1, 2, 3, 4, 5, instead 6, instead of 4. But if we would have rebalanced things out, we could have found a string that perfectly balances things out and generated this way. So this is the shallowest the tree could have possibly been if you generated 8 symbols. It could have been deeper than that, but the shallowest it could have been is 4 with 8 symbols.
The Chomsky normal form can always do that. Somehow.
If you have a grammar in Chomsky normal form, and you generate a string with 8 symbols, then when you look at the parse tree has a height of at least 4.
And it can always have 4 if it's a Chomsky normal form, is that correct?
No, there might be a string that requires you to have a height of 6. Like maybe this is the only way to generate this string with this grammar, and it doesn't have a height of 4. But I knew the height was at least 4.
Right, and this is for all context-free grammars?
This is for all context. We already proved that every context-free grammar can be converted to a logically equivalent one in Chomsky normal form.
Mm-hmm.
Once it's in Chomsky normal form, then when it generates a string with 8 symbols, it has a height of at least 4.
Okay.
If it generates a string of 2 symbols, what is its height at least?
1.
2. So if it generates 2 symbols, has a height of 2, at least. If it generates 4 symbols, has a height of 3, at least. If it generates 8 symbols, has a height of 4, at least. If it generates if it generates a string of length 16, it has a height of at least 5. Etc.
Oh, okay.
You with me?
Yep.
So the height of the string, for a string of length n, so if I want to generate n symbols here, then the height of that string is going to be at least greater than or equal to log base 2 of the string that we're talking about, and then plus 1 out here. So log base 2 of n plus 1. So when we were talking about 8, what's log base 2 of 8?
3.
3 plus 1 gets us 4. So this has a height of 4.
Okay.
Are we seeing the logic there? Because this is a crucial piece of logic.
What if you have a string of 5?
Well, if you have a string of 5,
Mm-hmm.
so let's do that really quick. Let's do one that has a string of 5. So this is the shallowest way we could have done 4 variables, right?
Mm-hmm.
Now to get 5, we have to do one more replace with 2 variables, and then go through and replace everything with the terminal. So then we replace with the terminal, 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 right? What's the height of the tree? 4.
I'm just saying, like, how does it work in your equation there?
Oh, thank you. Yeah, I was going to throw this in after the fact. It's going to be like that. It's going to be rounded up to the next integer. That's what that means.
Okay.
So now log base 2 of 5 is 2 point something. And then when you plus 1, you get 3.1. Or when you plus 1, that's going to be 3.1. Rounded up is 4. So your height is guaranteed to be greater than or equal to 4. 1, 2, 3, 4.
Okay, that makes sense.
Good there? Because this is a special insight that we're going to need. The height of your parse tree is going to act a lot in this case like the number of states acted in our previous pumping lemma. The same way that I was guaranteed a string of 0 to the p, 1 to the p looped somewhere, I may be guaranteed that a string of a certain length has a certain height parse tree, when it's in Chomsky normal form. And this is how we're going to say that, because the height always has to be greater than or equal to this number. So if I know the length of the string, I know the height is at least some number. The height of the parse tree. You with me? Okay, perfect. Last thing to notice is the height of the parse tree, 1, 2, 3, 4, is also the number of variables that you get in some chain. Remember, this one's a terminal, but this is a variable, 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 variable. So if you have a parse tree of height 4, that means you ultimately went through 4 variables to get to some terminal. Make sense? Okay, so those are the key things to notice about grammars in Chomsky normal form. Maybe write that over here to remind us that we talked about it. H is greater than or equal to the rounded up of log base 2 of n plus 1, where n is the length of the string you're generating. So the height of our parse tree is always greater than or equal to that. Okay, something else to notice about these parse trees. Here was our grammar. I meant for this to be in Chomsky normal form. It's not, but close enough. Still works for our example. And it generates this tree, right? And notice that we have this little subtree right here that I wrote out to the side. S goes to this end. So I took that and I put it here. The thing to notice is that this S ultimately generates another S somewhere down here. Forget the fact that S is a start variable. Pretend I didn't screw up and this isn't the start variable. The point is, whatever variable we have right here, we end up having that same variable here again. And so instead of in this parse tree, when we were generating this grammar, this S didn't have to ultimately generate an A and a B and then a 1 and a 0. This S could have instead generated an A and a B, where that B generated an S and an A, and that S generated an A and a B and an A, B and a B, and then ultimately generate that whole string. So this S didn't have to just generate this tree. We could have replaced this S with this S again and plugged that in right there to get a bigger parse tree. Right?
So you're saying note that in this one case S repeats, and that because of that you can continue repeating it?
Perfect. So when you have repeating variables in your parse tree, you can go to the top variable and replace the bottom variable with the parse tree that the top variable had. So I could rip this out, and I could have plugged that in right there and made my parse tree bigger. And then I could have ripped out this part of that tree and replaced it with that again. And I could rip out that part of that tree and replace it with that again, ad infinitum, as many times as I want. And it's still going to generate a valid string.
It's kind of like functions.
Well, this is how we're pumping up our string. This is our pump up process.
Why does the A go down to a 0 terminal on your picture on the right? It doesn't.
Because I screwed up. Thank you. Good catch. Because yeah, 1 1 0 0 0 is this 1 1 0 0 0. Good. But you understand what I'm saying, right? How this S didn't have to generate this. This S could have ultimately generated all this. And similarly, if we replace it with all that, we could do that again. And we could say rather than this S generating this S could have generated the same thing as this. And we can keep replacing those S's as many times as we want, generating bigger and bigger strings. And this is going to be similar to when we were talking about our previous pumping lemma. When we find a loop, we can take that loop as many times as we want. If we have repeating variables in a parse tree, we can keep replacing them with each other as much as we want, generating bigger and bigger trees. You with me?
Mm-hmm.
Okay, so that's the great insight we have. So, these pictures over here, over there, are meant to represent parse trees. So if I have a parse tree, S, and it's going along generating, and ultimately generates some variable R, and that variable R generating, ultimately generates another variable R, and then from that variable R we generate just a string X. From this variable R we generated a string VXY, where from S we generated UVXYZ, so this is our whole string W that we generated. We could have said instead of R just generating X, this R could have also generated VXY, same as this R. So we can replace it and make it look something like this. So that R still generates V, whatever that R does, and Y. But now this R, instead of just generating X, it generates VXY. And so, if we could have accepted the string W equal to UVXYZ, we could also accept the string W equal to UVVXYYZ. And we should be able to do that ad infinitum. We should be able to accept any string of the form UV to the n, XY to the n, Z, where n is any natural number. Notice we could also have gotten rid of the V and the Y. Because instead of replacing this R with this R, we could have replaced this R with this R. And that goes straight to generating an X. You see? So it's okay for the n here to be 0. So for any natural number, strings of this form should be accepted by our language. Okay? So, I don't think we need to do that example now. Let's just jump straight into it. Here's the beast, the pumping lemma. We're going to prove it. Here's what we're going to prove. If A is a context-free language, then there exists some number P and N called the pumping length, such that for all strings in the language of length at least P, we can divide that string up into parts U, V, X, Y, Z, such that the VY parts, the part that we end up having loop here, have a length of at least 1. The VXY part here has a length less than or equal to our pumping length. And most importantly, U, V to the n, X, Y to the n, Z is in our language for any natural number n. That's what we're going to prove. For any context language, this is the case. Wrapping your head around what we're trying to prove? Should we say it again? Maybe just jump into the proof, then go back and say it again? Not sure. Okay, so let A be a context-free language, and let G be the context-free grammar in Chomsky normal form, recognizing it. So we know that any context-free language A has a grammar in Chomsky normal form that recognizes it. We already proved that. Okay. Now, for any parse tree generating a string of length n, it must have a height of at least h plus 1, where h is equal to log base 2 of n. So I guess I did that a little bit different than we had over here. Sorry, should have looked closer to that. Okay? So now, let P, our pumping length, be 2 to the power of our number of variables, where V is the variables in our grammar G. So over here, in this grammar, how many variables did we have? We have 3 variables. So our pumping length for this grammar is going to be 2 to the power 3, or 8. And what we're going to notice is that any parse tree that generates a string of at least 8 with this grammar is going to have to use 4 variables. It's going to have a height of at least 4, so it's going to have to use at least 4 variables. So coming back up here, write this one in Chomsky normal form for an 8. Pretend that this is just a Chomsky normal form grammar. And we keep replacing variables with 2 variables, variables with 2 variables, variables with 2 variables, variables with 2 variables. And then finally, replace all our variables with a terminal. Maybe fill in the terminals. Notice that this is the shallowest possible tree we could have for a Chomsky normal form grammar generating a string of length 8. It's as shallow as it could have been, right? And what's the height of the tree? 4. And so we have to use 4 variables, at least 4 variables, for generating a symbol. The grammar only has 3 variables. We had to use at least 4 variables for generating the symbol. Therefore, we have a repeating variable. And with the repeating variable, we can start replacing. That's the key. Okay. So, maybe restart. Hopefully this is all clicking. Let A be a context-free language, and let G be the context-free grammar in Chomsky normal form, recognizing it. Then for any parse tree generating a string of length n, it must have a height of at least h plus 1, where h is a rounded up version of log base 2 of n. Let P, our pumping length, be 2 to the number of variables, where V is a set of variables in our grammar G. Then, for all strings in our language A that have length at least P, there exists a portion of S whose parse tree has a height of at least log base 2 of P plus 1. So, there was a portion of our string here, turned out to be our whole string, that had a height of at least 4. Over here, there's a portion of our string, not necessarily the whole string, so it's not this portion of the string, but there is some portion of the string like this that has a height of at least 4. Make sense? So, let's say it again. So for any string in our language that has length at least P, over there we've used 8, for any string that has length at least 8, there exists a portion of the string whose parse tree has a height of at least log base 2 of P, in our case 3 plus 1, which is equal to the number of variables plus 1. And so must have a repeating variable somewhere. Good? Now, let R be the lowest repeating variable, and let R star be the higher of the two. So going from the bottom of our tree, looking upwards, we're going to look for the first time we see a repeating variable. So we're going to come across some variable R, and we're going to come across some repeating variable R. We're going to call the higher of those two variables R star. So we're going to call this R and this R star. Okay. Oh, sorry. We're looking over here. So some portion of our string, whose parse tree has a height, where we're guaranteed there's a repeating variable. Going from the bottom up, we're going to look for the first repeating variable. So we see R here, we see another repeating variable, call R star here, and there we go. There's our first repeating variable. And that's what R and R star are. Right. So let R be the lowest repeating variable, and let R star be the higher of the two. Since R is a repeating variable, there must be two of them. We call the higher of the two R star. Good so far? Now this is going to follow exactly our picture overlay. Let S equal U, V, X, Y, Z. So we're going to break our string S up into 5 parts, U, V, X, Y, Z, where U and Z descend from S, but not R star. So U and Z descend from S, our start variable, but not from R star. Vy from R star, but not from R. So V comes from R star, Y comes from R star, but not from R. And X is a part of the string that comes from R. Good? Okay. Now we split up that way, we're going to show that they satisfy these 3 properties.
I'm a little bit stuck on step 6. I don't know. I get that you can divide the string into U, V, X, Y, Z, but I don't know how you can assign that V and Y are not part of, or U and Z are not part of R star, but are part of S and stuff like that.
So U and Z, U, since it's at the start of our string, it's going to be all of our string that ultimately came from S, but didn't come from R star at the start.
Okay.
And then Z is going to be at the back end. They could have been empty. So it's okay, U might have been the empty string, or Z might have been the empty string, would have been perfectly fine.
Okay.
And then, so they're descended from S, but not R star. Then V and Y are descended from R star, but not R. So V was generated from R star, but not from R, and Y was generated from R star, but not from R. Looking at our example up here, if we think about S and S as our repeating variable, then this right here is U, this right here is V, this right here is x, this right here is y, and this right here is z. This had our start variable as an ancestor, but not this s. So this we're calling our r star, and this we're calling our r. This portion had s, but not etc.
So u and z can be empty, but we're going to prove that v and y can't be actually.
V by itself might have been empty, and y by itself might have been empty, but both of them together can't be empty.
Okay.
And the reason that both of them can't be empty is because in replacing r star with some sequence of variables to r, I have to replace r star with at least 2 variables.
Right, okay.
And that other variable had to generate a terminal that wasn't generated by r.
Okay.
So since we're in Chomsky normal form, we're going to get that property.
Okay.
Okay, so good with 6 on the separation. So then we're up to 7. Observe that since r is the lowest repeating variable, the subtree of r star has height of at most v plus 1. Since r is the first repeating variable, going from the bottom up, then going from r star to r, that tree has to have a height of at most our number of variables plus 1. If it had our number of variables plus 2, then we would have had 2 repeating variables, and we didn't pick the first repeating variable. Does that one make sense? So going up our tree from r to r star, we had to use the first repeating variable. So how many variables could I possibly have counted going up the tree from r to r star? The most I could have counted is every variable and r twice.
Right, okay.
So that would have been all the variables plus 1, and so the most it could have possibly been is v plus 1. Now if your parse tree has a height of at most v plus 1, then the biggest string that could have been generated from r star down is length p. Because p is 2 to the v. Make sense? So if this vxy part right here had length 8, then this parse tree, right, let me say that differently. Let's pretend that we had a parse tree that just had 3 variables in it here. So going from r to r star here, we could have at most gone through 4 variables. R, some variable, back to r. Because it's our first repeating variable. So the height of this parse tree is 4. And so what's the widest this tree could possibly be, since it's in Chomsky normal form? If the height is 4, the widest it could possibly be is 8. It couldn't be any wider. Or in other words, 2 to the 4. Or in other words, 2 to the number of variables plus 1. So since r star to r, since the parse tree under r star has height of at most v plus 1, the string it generates has length of at most 2 to the v plus 1. Does that make sense?
I thought you just wrote 2 to the v there, and you're saying the length can be at most 2 to the v plus 1.
Oh, sorry. Yes. Let me say this right. Back to this example. So we have whatever we were looking at the symbol. This is r, this is a, this is b, this is r star. Right?
Mm-hmm.
Since this goes through 4 steps, the longest string it could have generated is 2 to the 3. So if this goes through v plus 1 steps, the longest string it could have generated is 2 to the size of v.
Okay.
Which is exactly what our p is. So that's what we're saying. So we're saying since vxy is ultimately generated from r star, and the height of r star's parse tree is at most v plus 1, then the biggest possible string you could have generated from r star is length p, or 2 to the v. Again, because it's in Chomsky normal form.
Right.
And so that's where we're going to get that the size of v, x, y altogether is less than or equal to p, which is this condition.
Okay.
Got that?
Yeah.
And then, observe that since G is in Chomsky normal form, R star must generate at least one symbol not generated by R. Right? Because you can't just replace R star with R, you have to replace R star with some variable and R. And that some variable has to ultimately generate a terminal too. So, since that's the case, then this V portion plus this Y portion must be at least one symbol. Could be more, but it has to be at least one. And so that's where we get this condition. And then finally, I already walked you through the third condition, but say it again. Observe that since R could potentially generate the subtree of R star, we could replace the subtree of R with R stars indefinitely. And so, u, v to the n, x, y to the n, z is in A, where n is any positive number, greater than or equal to 1. Finally, observe that we could replace R star's subtree with R, and so generate, in that case, u, x, z. Because this R star could have just generated x. It didn't have to generate v, x, y, it could have just done x. Because it can do the same thing R can do. Perfect. So, we've shown all three of those conditions. So therefore, there exists some number p in n, such that for any string in A with length at least p, there exists a way of dividing that string up into u, v, x, y, z, such that the vy part has length at least 1, that vxy part has length less than or equal to p, and u, v to the n, x, y to the n, z is in A for any natural number n. And that's the pumping lemma. So we just proved that this is true for any context-free language. Now, I'm trying to write it all out in one go. Sorry, it's really crammed in there. But thought it might help to see it all in one go. Let's just come back over here and then I'll erase and draw it up. Seems like I'll put that desk back anyways. Good enough. All right. So, writing the pumping lemma up all in one go. What did we just barely show? We just barely showed that there exists some number p, some pumping length p in n, such that for any string s in A, where the size of s is greater than or equal to p, there exists a way of splitting s up. There exists, what symbol do we start with? U. There exists u, v, x, y, z equal to s. There exists some way of dividing s up into u, v, x, y, z, where the size of the vy part is greater than or equal to 1, and the size of the xyz part, is less than or equal to p, such that for every natural number n, maybe put square brackets here, such that for all n in n, less than or equal to p, such that, how did I do it there? Did I put the square brackets at the very end? Yeah. Such that for all n in n, then u, v to the n, x, y to the n, z is also in A. Okay, there's a mouthful. Drew way too big at the start. Sorry. Now, we use the pumping lemma to prove that a language is not context-free. So remember, if it's a context-free language, that implies it has this pumping property. We're going to use the converse. we're going to show not having that pumping property implies it is not a context-free language. So now we need to be able to understand what it means, what the negation of this is. So now I need to negate this thing. What's the negation of that? What's not the pumping property? That is that for all p in n, for any natural number you choose, comma, there exists a string s in A with size at least p, such that for any way you split it up, for any u, v, x, y, z equal to s, for any way you split it up, as long as you make sure that the v, y part is greater than or equal to 1, and the x, y, z part is less than or equal to p, comma, then there exists some n, I can find some length to pump it up to, such that u, v to the n, x, y to the n, z is not in A. And that's the converse of the pumping lemma. Or that's the negation of this. So to show that something is not a context-free language, we show that this applies to it. If I can show that for some language, no matter what length p you choose, I can always find some string in the language of that length, such that no matter how you divide up the string, as long as you divide it up satisfying these, I can find some number to pump it up to, such that the string pumped up that number is no longer in the language. So if I can do that, I show that the language doesn't have the pumping property, and therefore it's not a context-free language. Because every context-free language has this pumping property. Does that make sense? And so ultimately, that's what we would use to show 0 to the n, 1 to the n, 0 to the n is not context-free. So we'll pick it up next time doing this exact proof, proving that that is not a context-free language, using the pumping lemma. Okay? Yeah, I know that's a mouthful. It's a lot to sink into. Again, it's all in the book. You can read the book, read the pumping lemma. It's one of the most crucial lemmas there are, so try and soak it in the best you can.
Part of me was hoping that it wasn't that important.
No, it is that important, which is why we spend a lot of time on the pumping lemma. We spent a lot of time on the previous pumping lemma to try and prepare you for this pumping lemma, because this is how we classify languages as not context-free languages. Which ultimately, that's what almost all context-free, or almost all computation theory is, just classifying problems. How hard is this problem? Is it really easy? Is it really hard? Is it impossible for a computer to do? And that's a lot of what computation theory is. What can and cannot be done by certain types of machines? Or, if it can be done by a machine, how hard is it to do? Theoretically, how hard? What are the theoretical limits on solving problems? And we'll get to that once we get to first what they can and can't do, then we'll get more into complexity theory, where we can talk about some really cool problems. Anyways, that's all we have for today.